Hello. So me and Kamil here are going to be presenting today a small presentation about smart contracts testing. That's us. And what we do daily is we're software engineers, as Soto mentioned. We're kind of in the crypto division of the company because the company also does React Native. And we are developing many dev tools for Starknet, which you may be familiar with, and also sometimes posting memes on X. So what we do daily with Starkware is Starknet developer tools, so like SDKs, package manager, profiling tools, and most importantly for this presentation, a testing framework, which is Starknet-Foundry. You might be familiar with it because it's similar to the Ethereum's Foundry. It's a testing framework built on top of the native test runner, which the Cairo language, which Starknet uses, has. And yeah, obviously it's inspired heavily by Ethereum's Foundry also, but we do have like our own things sprinkled on top. It facilitates more testing modes than the vanilla testing runner. And we mainly focus on developer experience and many testing vectors for the smart contracts. So let's just take a step back and ask ourselves, why do we even write tests? So mainly it's to ensure that what you wrote is correct, so you didn't write anything dumb. It's also for documentation purposes, so when a developer comes and reads the test, he basically knows what the program is supposed to do without like guessing. For regression prevention, when you upgrade your smart contract, you want to make sure that basically everything that you wrote before isn't going to break. And like the general feeling of security that you have more confidence to deploy on the mainnet when you have a well-tested program. So is smart contract testing any different than testing like normal, regular programs? So they are immutable, so that's kind of one thing that you have to take into account when writing tests, because like the consequences can be quite daunting, especially if the contract doesn't implement any upgradability. They're often open source, so you have to take into account as well that somebody can read through the code and reverse engineer it, try to perhaps find a security hole in it. So the stakes are much higher. Usually, if a smart contract has a security hole, you fight about it in the worst way possible, and it's often too late. So there's also a lot of interaction between unknown components. So, for example, when you're designing and implementing an account, you have to take into account some of the interactions that might be possible between accounts and other regular contracts. And there are multiple possible testing vectors on different abstraction levels, so you can basically test the internals of the contract, the interface, the interactions, like I said, and I don't think that's really common in testing like normal programs. So there are some limitations to testing blockchain-based apps and smart contracts, obviously, which is one of which is transaction finality. You have to do, like, especially on L2s, take into account that the fact that the transaction has been accepted by a node doesn't mean that it will actually go through. Testing the contract internals is more difficult than testing internals of your programs written in other languages. Constraints of the blockchain, you can't do some stuff on the blockchain that you could normally do with a regular program, like setting the date or setting the block number is sometimes impossible. There is also a lot of language friction of testing tools, especially when you take into account like hard hat. It has to be written in JavaScript, and like obviously you don't write in JavaScript for Ethereum, you write in Solidity. And there is a general lack of mature tooling and good practices, like the previous presenter said about the UX. There is a lot more to come in terms of good practices when testing the blockchain apps.
So we've all heard for sure about smart contracts getting hacked. It's not like it's something unusual. So it's not hard to find many headlines about the millions of dollars that get lost weekly and monthly. So it's definitely a big risk when deploying smart contracts and caring for their security. So yeah, what to do if your contract gets hacked? That's the question. And to be honest, not much you can do actually. At least not in terms of like recovering the lost funds. It's not like it's say a bank in Web2 space where you can just cancel the stolen funds and add the money out of thin air or revert to previous snapshot. But there were some specific cases in the past, and most of you, I suppose, probably have heard about the infamous DAO hack. It was a smart contract that in 2016 contained approximately 15% of all the ETH supply. It was hacked for over $50 million. And the community of Ethereum decided that they should do the hard fork on the chain and like overwrite the history to remove the hack that actually happened. What is interesting is that the original chain with the bug in this DAO smart contract actually kept growing, and the blocks are minted till this day. So whether it is something that we're allowed to do in the blockchain space is like a big debate in the community. Some say that it is the code is the law, so no theft has been made because somebody just inspected the code carefully and did what it said. But others say that it was absolutely okay in this specific case because so much ETH has been stolen. But yeah, it is an extreme case and pretty unlikely unless you control like half of the nodes in the network. It probably won't happen when your smart contract gets exploited. What else? Well, you could contain the damage. So if your contract implements like a pause functionality, there is one from OpenZeppelin that's nice to use. So we could pause the contract or maybe use some access control to restrict who can access it. You could mitigate further losses. So move, if feasible, of course, move the remaining funds to a secure address that the attacker cannot access. Or if the draining of the tokens hasn't happened all at once, you could play kind of this good hacker and do exactly what the attacker did. So use the same exploit to try to save as much money as possible. Of course, you could later learn from your mistakes, analyze what actually went wrong, and in the end, you could go cry in the corner due to your lost money. Okay, so what are some most common vulnerabilities? We could actually have a whole list, but let's quickly go through some of them. Some like the most common. So of course we've got logic errors. These are like basic business logic errors when the contract does something like not intended actually to do. We've got bad arithmetics. So for example, not all ERC20 tokens have the same number of decimals. By default, they have 18, but for example, USDC and Tether have 6. So you have to take that into account when you're doing some math on them. Access control, so not authorizing the caller, also some unprotected external functions. Reentrancy, so basically when function allows the caller to recursively call it without the function actually fully exiting. And this is actually how the DAO lost, this is actually the vulnerability from the DAO. Integer overflow, so I suppose we all know about that. When we try to increase the max value of integer by 1, we go all the down to the lowest possible variable. Oracle manipulation, so when some dApps depend on external data, off-chain data, there is, of course, a risk when the data could be malicious or straight invalid, and bad randomness, meaning that using for the source of randomness some bad data on chain that could be tampered with or manipulated by some third party.
So there are many applicable flavors of testing. We're going to talk about some of them, not all of them necessarily. First of all, all of you know is unit testing. It's the old reliable of the pack, and those tests are meant to be fast, fine-grained, so testing the smallest possible pieces of code. Those are the things that we use to test the internals of the program. They should be reliable, so you don't have like unexpected failures from them. And most of all should be simple, because like they are testing only the base layer. Second one is integration testing. So you can see here what can happen when you don't integration test your contract. Basically, you test a lot of pieces of small code, but when you fit them together, it doesn't quite work. So there can be many interactions between smart contracts, like contract to contract or user to contract, and this is the scope that we are focusing on when integration testing. They're reasonably fast comparing to unit tests and like the more advanced end-to-end tests. They are testing interfaces, like for example in Foundry we define integration testing and as calling some interface, and then the contract calls other contract, etc. They are medium-grained, and usually there are some mocks involved because like there's this contract interaction that sometimes you cannot predict. So you want to put mocks in the system. End-to-end testing, which I mentioned before, is basically testing your dApp end-to-end, interface, contract, etc. There is this UI and contract interface integration, testing the UX, and you can, like one scenario can contain one or multiple transactions or like whole flow, basically. Like you might want to test like your onboarding flow or something like that. It is the most difficult to achieve efficient setup, and those tests are usually the slowest. And I think it's most common to omit them at all when testing, which is, I think, not a good idea. They're slowest of the bunch. So there is this thing called fork testing. Specifically in Foundry, we do fork testing. So normally when you have a standard test, you have a test that communicates with the local state, and that's basically the data flow that you're going to get. But with the fork test, you communicate with a proxy, which pulls the data from the main net, caches it in the local state, and then basically works on that. So you don't work on the state on like testnet or something like that. You have a replicable flow, repeatable tests, and you test on the real data, so the setup is much easier. Yeah, it's forking state of the chain, obviously. You can choose the chain as you want. It's easier to set up the dependencies, so other contracts that are on the chain. Yeah, it's real environment testing, so basically you could fork mainnet and see if it all is going to fit together well. It is applicable to some unit tests, but mostly we use that for integration testing and end-to-end testing. And those tests can be made relatively stable by locking the block number that you are pulling from, so it doesn't like break randomly on the CI, whether you want to pull the latest block and something in the state changes that you don't expect. Also, we do have some utilities for testing gas, which is kind of important because like you don't want the user to pay like $1 million for buying an NFT or performing some simple action in your app. It's like benchmarking, but for cost. Basically, it's meant to find unexpected cost spikes in your application. By testing multiple parameters, you can easily achieve that. It's making sure that app is as cheap as possible for the user, because that's what we care about as well as smart contract developers. And it's easy to define some boundaries that you don't want to exceed. And obviously, if someone does a change that makes the cost exceed, it's easy to spot because the tests are meant to detect regression. Yeah, it's worth to test the whole scenarios. So we want to test like basically maybe an onboarding flow or like a basic flow in your application to make sure that it's not ridiculously expensive. So there is a hot topic also in smart contract testing, which I don't think is relevant in normal testing. I don't think I noticed that. Is the fuzzing and parametric testing, not so much, but the fuzzing especially. So standard test is like comprised of the three main components. You do a setup, run the test, make some assertions, simple. But the fuzz test is basically adding a loop for the case, which generates the inputs in some arbitrary way. So those inputs are random-ish, let's say. They try to find a falsifying example for your test case. So basically, it's trying as best as they can to find an example that doesn't satisfy the constraints. And there are many strategies and engines available around. Depends on what tool you're using for fuzzing. They're usually slower to execute because you're running many test cases, and you want to make sure that you're running them on the right ones when you need the most coverage of the parameters. And thus, they are not as stable as other tests because of the randomness, and because like the fuzzing engines sometimes can be not deterministic.
Okay, so up next we've got invariant testing. And to talk about invariant testing, we would need to know what invariants actually are. And invariants are properties of the program that should always hold true during the whole execution. So an example invariant could be that the sum of all user balances is equal to the total supply for some token contract. It could be that user can only withdraw what they deposit, or it could be as simple as some variable is always less than 3, let's say. So with these invariants that we have for our contract, for our functions, invariant testing is going to try to break these properties. And how is it going to do that? Well, it's going to use what Tomek just talked about, the fuzzer. Here is a little demonstration. So the fuzzer basically is going to throw random inputs into our function, and with the goal of breaking these invariants that we've set on previously. So here we can talk about two types of this fuzzing. One is what was previously, which is stateless fuzzing, just random inputs to functions. And another one, maybe a slight level of abstraction higher, would be stateful fuzzing, which not only chooses random inputs to some function, but also chooses many different functions in our smart contract. So we could think of it also as just random transactions to our smart contract, so that the state is preserved between these runs. Up next, we've got differential testing, maybe a bit intimidating name, but it's fundamentally pretty simple. So suppose we have some function specification f, and then for this function specification, we've got two implementations, f1 and f2. Now, we would like to, since these functions implement both the same specification, we expect them to behave the same. So, to be more precise, we expect for all inputs, that the outputs of both of these functions will be the same. And of course, we expect for no input the output to be different. So pretty much it's this image, right? So we test both implementations and check whether they are the same. Great. So now with this base of differential testing, we could have some, could do some expanding, some more fun stuff. So for example, we could expand it easily to multiple implementations. It doesn't have to be just two implementations. So we assert all of them at once. We could ask whether if the results are the same, is the behavior the same of these functions? So we could also check the traces or check the side effects like emitting events or reverts. We could have differential fuzzing. So we could again use the fuzzer to find inputs that would break the equality. A nice thing is that nothing really forbids us from using two different languages to test the implementation. So we could have like one implementation in Solidity and second one in Python. And so an example use case would be when we're comparing an upgraded, maybe optimized implementation of some straightforward function. It's often the case that when we optimize for gas and costs, these functions, they get a bit, we do like some tricky stuff, and so it's not as straightforward. So it's nice to have like a differential test for these functions. And also when we test our own implementation against some known reference implementation. Up next, static analysis. So up to this point, we've been talking about dynamic analysis, dynamic testing. So we've actually been running the code that we have to perform the test. But here we have static testing. So at a high level, it basically comes down to looking at the code or using a tool to look for us. Basically, when we use static analysis, we look for common vulnerabilities and pieces of the code that are considered bad practice. And so some of the modern tools that are out there can, for example, detect reentrancy, access control issues, and some other vulnerabilities we've talked about. But sometimes one flaw with them is that sometimes they give like false positives for your code, so your code could be perfectly valid, but the tools would like flag the part of the code as potential, that it would have a potential issue. And at last, we have formal verification, which, as the definition says, it's act of proving or disproving a property of the system, usually done through a mathematical model. So again, we're talking about some property of the system. Also like property invariant. These are like common words. And so formal verification has many different techniques. Some of them include symbolic execution, abstract interpretation, and model checking. And the one we'd like to talk about briefly is symbolic execution. It has the most use in Web3 space. So at a high level, what symbolic execution will do is explore all the different branches and paths our software can take, convert them into mathematical expressions. Then with these mathematical expressions, it's going to dump all this math into something that's called SMT solver. And in the end, we're going to ask the solver whether our property, which we've defined, or the invariant, whether there exists an input that breaks this property. And so, of course, as all things, this too has its limitations. First is that we don't really know what the right questions are to ask the solver, because yes, formal verification is great, but we need to come up with the actual properties, the invariants, for the solver to give us a mathematical guarantee that, yes, this property is in fact true for the whole execution of the program. The computation is often heavy, and sometimes it is infeasible. And also it requires significant effort and some knowledge about. Okay, so some key takeaways will be that there are many testing patterns out there. We haven't talked about each and every one, and new ones occasionally are created. There, unfortunately, exists no silver bullet, no method to rule them all. So to cover all bases, it's best to use like a variety of them. And of course, that different methods are best suited to find different types of bugs. Okay, great. So that's pretty much all we've wanted to share with you. As a closing thought, let's hope that our future tests will work better than this guardware here. Thank you.
We encourage you to follow us to see some of our memes. We try to be funny. Any questions?
Thanks for the nice presentation. My question would be regarding differential testing. I think it's very interesting and not sure. Are you aware that anyone has used this, for example, when porting Solidity project to Cairo? For example, if you have like I don't know, some port of Uniswap or Aave or whatever, and then is it even like I think it could be an interesting use case to be pretty sure that the functionality of the functions is more or less the same. So that's one use case that I'm thinking, and the second is, for example, for bridges that would want to bridge from Ethereum to Starknet. Also, you have similar implementations on both sides, Solidity Cairo, and probably these differential tests could be used for this as well. So, are you maybe aware that any company or project has done this?
I personally am not aware about any project that has used this. They might have, I'm just not aware. But also, I feel like differential testing is not that popularized. And so, that's why also we're talking about it, so more people know.
So there is no specific tool that enables it currently on the Starknet ecosystem that I know of, but probably. Yeah, probably a good idea to add it. We do have a lot of ideas. There are a lot of testing patterns that we haven't done yet, and we'd like to provide as many of them to the users as possible. But I think in some form, perhaps I saw the code bases that used the testing, as Kamil said, from the both sides. So they wrote like the Foundry tests and the Python tests to basically test like both sides to assess if the results are the same. But it's also more kind of manual approach, not the automated one, and not organized into nice patterns. Any more questions?
Hi, thank you for presentation. So regard the things when the hack happens, just want to add 3 things. Recently, I was helping to the small protocol that was hacked. So what was happened in that moment, we got information that white hats are available through the Telegram channel SEAL 911. So basically, a lot of good guys are behind that channel, and they are supportive in a way that they can help with tracking the funds, and they are connected with centralized exchanges and things. So if someone went into that situation, that channel is really helpful. So that's one information. Second thing that the protocol owners did do is just send the message through the Etherscan to the hacker. And in this particular situation, it was really they were really lucky because the hacker accepted the bounty of 10% of the hacked funds and returned everything back. And the third thing is that hacker, there are tools that are really tracking the wallets, right? And are also connected to some centralized entities. And it was obvious that this address that hacked the protocol made a lot of deposit withdrawals with centralized entities. So that's just addition to those slides where you were talking about it. So this wasn't question, it was just addition. So sorry if I
no problem.
Trying to be smart, but this is my experience. Yeah.
Interesting, interesting example of goodwill. I wouldn't do that.
Well, it turned out to be good at the end, but yeah.
Nice.
Thank you.
Thanks.
Okay, thank you.